Exercises 5 Solutions, Nuclear Properties and the Birth of Atoms. Number 1. Explain the role that the electric force plays in binding the atom together. 2. Explain the role that the strong nuclear force plays in the nucleus. Why is a nuclear bomb really an electrical bomb? The electric force binds the atom together because protons in the nucleus have a positive charge while electrons have a negative charge. This creates an attractive electrical force between these two that electrically bind them together. When one looks inside the nucleus, however, it is categorically quite different. The nucleus is composed of positively charged protons and neutral neutrons. Therefore, no attractive electrical force can bind the nucleus together. Something completely new must be at work. This new force is a residual force of the QCD force, the force of quarks inside of protons and neutrons. So when you look at a proton or neutron, a nucleon, the stuff that leaks outside this residual force is what they call the strong nuclear force. And what we found about this residual force is that it binds protons and neutrons alike. So if I have a depiction of the picture here, if I have two protons, two neutrons, or a proton and a neutron, that residual force binds the protons, the neutrons, and the proton-neutron combination with exactly the same strength. Therefore, from a macro viewpoint, the strong nuclear force is what binds neutrons and protons together inside the nucleus. The last part of the question is, why is a nuclear bomb really an electrical bomb? In my lecture on this material, there are two ways to view this, either using the force or energy picture. What we know is that uranium is the last atom on the periodic table that exists naturally. This means that its nucleus has 146 neutrons, 92 protons. Now imagine that this is the nucleus that contains 146 neutrons, 92 protons. What we know is that the red protons have a very, very strong electrical repulsive force now. The attractive, strong nuclear force is barely able to contain all that repulsive electrical force. A slight agitation by a slow neutron capture, causes fission to occur, and the strong force cannot contain anymore the very strong repulsive electrical energy of the nucleus. Therefore, the nucleus splits. That means if I start off with some uranium isotope, typically uranium-236, there's a release of neutrons plus other energy. But the more important thing here is that these two nuclear fragments are positively charged and they repel each other very, 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 very strongly. So that means most of the energy goes into this electrical repulsion between these two fragments. Therefore, a nuclear bomb releases primarily electrical energy. Written out, a nuclear bomb releases electrical energy mostly contained in these two fragments. 2. Why does a neutron make a better nuclear bullet than a proton or an electron? If one shoots a positive proton at the nucleus, the positive proton will be strongly deflected by the repulsive electric force of the positive nucleus. It follows this deflected path, and as a consequence, the proton never reaches the nucleus. So it's not a good bullet. On the other hand, we just discussed the role of the electric force for the atom. If one shoots an electron at a nuclei, the positive electric force of the nucleus will most likely capture the negatively charged electron. But bound electrons then accelerate and emit radiation. That is, if I shoot an electron, you could imagine that this electron is captured and it's now in orbit. But as it orbits, it's going to be emitting radiation, and therefore it actually will de-excite and not be able to really reach the nucleus. So the electron is not a good bullet for the nucleus. If you want to get into the nucleus, you need to shoot a neutral neutron because they do not feel the repulsive electric force. So if it's not deflected, then I can get neutron capture, And then I could start something like fission or something like that. So the neutron is the perfect bullet for the nucleus. 3. Explain the band stability. In other words, as the number of protons increases in the nucleus, the number of neutrons has to increase even more so. Why is this so? The band or line of stability is this black line that runs through the graph, which represents all stable nuclei. What this graph shows is that for nuclei with atomic number less than 20, these nuclei are stable when their neutron-proton ratio is closest to 1. In other words, the number of neutrons to protons, or n/p, is 1. If I have atomic number between 20 and 83, nuclei are most stable when their neutron to proton ratio is about 1.2 for midweight, sort of like in the metals like copper and stuff like that, all the way to the really heavy nuclei where their neutron proton ratios are about 1.5. This would be sort of like lead. What this means is that as nuclei get heavier, they require more neutrons than protons to be stable. Why? Adding more protons increases the repulsive electrical force, making the nucleus even more stable. By adding more neutrons, it does not increase the electric force, it increases the strong nuclear force by creating more nuclear bonds. 4. Why do alpha and beta decay produce new elements, but gamma decays do not? And alpha decay usually occurs to heavier nuclei, and we remember that on the band of stability, it's typically this yellow region that actually sees alpha decays. An alpha decay is when an unstable nuclei emits an alpha particle, and an alpha particle is a helium nuclei, which is 2 protons, 2 neutrons. One example of an alpha decay is 238 uranium going to 234 thorium. And what you're seeing here is that uranium-238 is being reduced its atomic mass by 4 and its atomic number by 2. But if the atomic number changes, it's a different element. Written out, since alpha decays change the atomic number by 2, the decay changes the element type. So I have a different element. In beta and inverse beta decays, we have a neutron turning into a proton, plus emitting a beta minus, plus energy. This is beta decay. And in inverse beta decay, we have a proton that's decaying into a neutron, plus a beta plus particle, plus energy. Although the atomic mass does not change in each of these situations, but in beta decay, the fact that I get an extra proton, there's an increase in the number of protons, means that I've changed the element. Whereas in inverse beta decay, instead of increasing, I'm decreasing the number of protons. Once again, I changed the element. For example, if I have a beta decay of carbon-14, you could see that carbon-14, although its atomic number doesn't change, although its atomic mass does not change, you do see that the atomic number increases by 1. But if I increase by 1, I go from carbon to nitrogen. In inverse beta decay, I start off with fluorine 18, and what you're seeing here is that the atomic number has decreased by 1, so therefore I get oxygen 18. The 3 most common type of nuclear decays, alpha, beta, gamma, only gamma decays do not change the type of nuclei. And what we said here is that the nucleons and nuclei live in energy levels just like electrons do in atoms. So if a nucleon, a neutron or a proton falls from a higher to a lower energy level, it emits a gamma ray. So there isn't a change in the number of protons or the atomic number. It's just an excited state going to a de-excited state. And the example that we did here is that we actually looked at an excited state of titanium. And what we found here is that it then jumps from a higher to a lower energy level, and it does not change type. When discussing fission and fusion, the question is whether energy is released during the process of splitting nuclei or joining them together. Elements lighter than the iron group can release energy through fusing together. Elements heavier than iron can release energy through fission. Explain what this means. So here to my right here, what you're seeing here is that I have highlighted in green the bottom or the most tightly bound nuclei around iron. And to the left of iron is fusion, to the right of iron is fission. To the left of the green line, separate nuclei have higher energies, while a nuclei created by fusing two lighter nuclei have a lower binding energy overall. One example of nuclear fusion is that in the core of stars, if I have a proton or hydrogen 1 ion and deuterium, hydrogen 2, when these are fused together, you produce helium 3 plus the release of this gamma. So if I look at the binding energies, I see that the binding energy of hydrogen is 0. The binding energy of deuterium, hydrogen 2, is about -1. So the combination of these two here reads -1. Now if I look at the binding energy of helium 3, we could see that it looks like it's just about 3 here. So when I compare -1 to -3, -3 is a lower number, -1 is a higher number. Therefore, this has a lower binding energy. And if I now normalize this to a standard energy bar diagram like we did in the chapter on energy, we get that the binding energy of hydrogen and hydrogen 2 is bigger than the binding energy of helium 3, and it's this energy difference that's the energy released in fusion. That's why in fusion you get energy release. Again, starting with the binding energy curve, we see that the bottom of the well is the iron group of nuclei that have the deepest swell, and this is to the right where fission occurs. Fused nuclei heavier than iron has nuclei move up the binding energy curve, but this requires an input of energy since these nuclei have higher binding energies overall than iron. So moving up this thing requires energy input. It does not happen spontaneously. But going from a lower to a higher binding energy cannot release energy. This implies that no atoms or nuclei heavier than iron can undergo fusion. 6. By looking at the binding energy per nuclei, which nuclei will be harder to split apart? Why is it that when nuclear fusion occurs, their products move towards the iron group? So immediately I have the binding energy curve right here, and I set up my green line. To the left is fusion, to the right is fission. Starting with the binding energy curve, only nuclei to the right of the green line can undergo nuclear fission. That is, they split from higher to lower binding energy states. The example we looked at in lecture was the fission of uranium-236. In this example, we shot a neutron to uranium-235, which caused neutron capture and created 236 uranium. This is highly unstable, so when you looked at 236, it immediately underwent fission that split into barium and krypton while releasing neutrons and energy. Let's look at this fusion reaction on the binding energy curve. So if I start off at 236, which is somewhere around right here, what you're seeing here is that when it fissions, it splits into 144 barium and 89 krypton. You could see that they're moving towards a lower binding energy, meaning that they're more tightly bound here. So if I start out here at 236 uranium, Then as it undergoes fission, it moves towards the iron group because it's higher up, and so therefore it could go to these lower binding energies here. So if I start off with nuclei around iron, just above iron, they're closer to this iron group. So they don't have as much room to decay downwards as, let's say, up here at 236. So because this group here is closer to the iron group, fission will be harder because they have less room to fission. On the other hand, fission always moves down towards the iron group as the binding energy curves. So since fission is to the left, as things fuse, their binding energies hit rock bottom down here. So they always slide in this direction. So they always move in this direction because that's where the lowest binding energy is at, or the deepest well. Question 7. The Earth is not capable of producing gold atoms. Explain how gold atoms in a gold finger ring were produced using the Big Bang, stars, and supernova nucleosynthesis. Big Bang nucleosynthesis. When the Big Bang occurred, only the first 4 elements were produced. Hydrogen was roughly 75%, helium at 25%, lithium and beryllium were created in trace amounts. Stellar nuclear synthesis. After around 20 million years after the Big Bang, large clouds of hydrogen were clumped together by gravity to form stars. With extreme pressures and temperatures at their cores, nuclear fusion started. That means hydrogen was used to fuse into helium. And then hydrogen and helium can be fused to produce lithium. And then when a star runs out of hydrogen, it starts fusing helium. So if I fuse helium and helium together, I get beryllium. The bottom line here is that I could now start moving up the periodic table. So from our previous discussion, these are the elements formed by nuclear fusion in stars. So I could keep moving up this table here, and for example, our sun can only fuse up to oxygen because it doesn't have enough pressure and temperature inside to cause fusion of higher elements. We go along here until we get to iron. Iron is the last nuclei made in stars through fusion. Stars cannot make elements heavier than the iron group because iron is the nuclear ash of stars, cannot fuse atoms of iron. So in summary, stellar nuclear synthesis can only produce elements from helium to iron, from 2 to 26. Supernova nucleosynthesis. Any element heavier than iron is most likely produced by a large star going supernova. A supernova is an exploding star that has access to enormous amounts of energy. There are multiple processes that create atoms heavier than iron, but the 2 main ones are the R process, the rapid process, and S, the slow process. During the collapse explosion process of the supernova, very rapid processes can create atoms with atomic numbers greater than 26. About half of them are created during this time. During the expansion part of the explosion, slower processes create the other half of atoms heavier than 26. Since gold, as well as copper and silver, are above atomic number 26, they are made from exploding stars. So, the gold wedding band that I currently wear is made from stardust.